We are from Group 7 and we are going to present our project on Chapter 4, Multiple Integral for the subject Multivariable Calculus. Question 2C until A until C. Let me introduce our team. I'm Alexander Kwek Hai Sheng, CE 240071. Then Muhammad Afiq Ihsan bin Muhammad Sahuri, CE 240217. Muhammad Ibrahim Alham, Muhammad Zameh, CE 240240. And finally Osama TK Mintit, AE 230095. Together, we have worked on applying multivariable calculus concepts, specifically focusing on multiple integrals using MATLAB. The main objective of our project are to apply multivariable integration techniques to solve complex problems involving double integrals, to visualize region surface using MATLAB, to verify symbolic results and interpret graphical outputs. This helps deepen our understanding of calculus applications in real-world problems. For our project, we use MATLAB as the primary tool. Why MATLAB? It supports symbolic computation using commands like sims and int, which is symbolic variables integral. It offers powerful 2D and 3D graphing capabilities and allows script automation, ensuring consistent, accurate results. These features made by MATLAB ideal for both analytical and visual aspects of our calculus project.
Hello everyone, today I will explain how we solve this double integral by using polar coordinates. So we are given the double integral 0 to 2, 0 to root 4 minus x squared plus y squared dy dx will become r squared equal x squared plus y squared. So we have here root 4 will become 2 and y will become root 2 power 2 minus x squared. So the integral will become pi over 2, 0 to pi over 2, 0 to 2, r square r d theta. Then we substitute normal integral. Then we will get the final answer 2 pi. So after we finish it of the manual calculation, we move to the software. I do the software by using MATLAB application. I'm calculating a double integral of function fxy, x squared y squared over quarter circle region. First, I defined x and y as symbolic variables. Then I created function of x squared y squared. The integral taken two steps. Integral with respect y from 0 to root x squared minus 4, and the outer integral is with respect x from 0 to 2. This region forms a quarter of a circle with radius 2, located in first quadrant. After calculating the symbolic result, I printed it using printf and also display numerical value by converting it with double function. This allow us to see both and exact abundance value of integral. To visualize the function and region of integration, I used two supports. The first support is the 3D bolt of a function zx plus x squared y squared over the square region from 0 to 2. In both x and y, this series show how we can function increase as we move away from the origin. The second suppose the show is the 3D region of integration, a quarter circle I generated using polar coordinates, filling the area with second color. This bolt help us to see clearly where the integration is happening. Together both plots give full picture the 3D square where the integration under and the and the 2D region we are integration over. That's all for me. Thank you so much for your attention.
For the manual calculation of question B, we are asked to evaluate the double integral of the function e to the power of negative x squared plus y squared, written as exponent negative x squared plus y squared, over a circular region with a radius of 2 centered at the origin. Because of the circular symmetry of both the function and the region, it is more convenient to solve this integral using polar coordinates instead of Cartesian. In polar form, the expression x squared plus y squared becomes r squared, and the area element dx dy become r d theta. So the integrand becomes exponent negative r squared times r. The limit of integration for r go from 0 to 2 and for theta from 0 to 2 pi. This set up our double integral as the integral from 0 to 2 pi of the integral from 0 to 2 of r times exponent negative r squared dr d theta. To evaluate the inner integral, we use substitution. Let u equal to r squared, so du equal to 2r dr. That's mean r dr become du over 2 and the new limits for u go from 0 to 4. So the integral become 1/2 times the integral from 0 to 4 of exponent negative u du, which evaluate to 1/2 times the quantity 1 minus e to the negative 4. Finally, we multiply these 2 pi from the outer theta integral and the final answer is pi times 1 minus e to the power of negative 4. Assalamualaikum and hi everyone. In this video, I will explain my solution for question B, which is involve calculating a double integral and visualizing it using MATLAB. First, the goal is to evaluate the double integral of the function fxy equal to exponent x square plus y square over a circular region of radius 2 centered at the origin. Because the region is circular and the function is radially symmetric, it's more efficient to convert the integral into polar coordinate. So, I define the symbolic variable r and theta in MATLAB and rewrote the function as r over theta equal to exponent negative r square c dot r. The extra r comes from the Jacobian when converting Cartesian to polar coordinate. Then, I integrate this expression first with respect to r from 0 to 2, and then with respect to theta from 0 to 2 pi. The result from MATLAB was a clean symbolic answer. Lambda over pi bracket 1 minus exponent negative 4 lambda, and the numeric approximation is around 3.085. Next, I include two graphs to better understand the problem. The first is a 2D plot showing the region of integration filled circle of radius 2. This helps visualize the domain over which the function is being integrated. The second is a 3D surface plot of the function fxy equal to exponent negative x square plus y square. It looks like a smooth bell shape with the highest point at the center and gradually decreasing outward. By combining symbolic integration with polar coordinate and clear graphical visualization, this approach provides both an exact solution and an intuitive understanding of the integral.
My name is Muhammad Ibrahim Adham. For this problem, question C, this problem involves evaluating a double integral over semicircular region. The original integral is in Cartesian coordinate, but because the region is semicircle of radius 2, it's easier to use polar coordinate. In polar form, x square plus y square equal to r square. Then the integral becomes 1 plus r square. We set the limit r goes to 0 to 2 and theta goes from 0 to pi. The integral is multiplied by r in polar coordinate, so the expression becomes r multiplied by 1 plus r square. We integrate first with respect of r, getting r square over 2 plus r power of 4 over 4. Evaluate from 0 to 2. That gives us 6. Then we integrate respect to theta, which gives us the final answer is 6 pi. Thank you. In question C, we are required to evaluate the double integral of the function f as y equal to 1 plus x square over y square over the specific region of R, which is the upper half of circle with radius 2. Center of the origin. To solve this, the function is defined symbolically in MATLAB, and the integration is performed in Cartesian coordinate. The limit of integration for y are from 0 to sec 4 minus x squared, representing the upper semicircle, while s range from negative 2 to 2. The double integral referred to dy and ds is calculated both symbolically and numerically in MATLAB. giving a final result of 6 pi, which is approximately 18.8496. To support the understanding of the region and the surface being integrated, two graphs are plotted. The 2D plot display the region of integration in magenta, clearly showing the upper semicircular area. The 3D plot illustrates the surface z equal to 1 plus x squared plus y squared are parabolic that rise as s and y increase. This visualization helps in comprehending the shape of the function and the area over which the integration is performed, verifying that the integral is correctly evaluated over the intended region. Thank you. To conclude, we successfully applied multivariable integration technique to solve the given problems. We verified both symbolic and numerical results using MATLAB. We enhanced our understanding of region visualization and 3D modeling. And most importantly, we practiced effective teamwork and collaborative problem solving. This project has been a valuable learning experience for all of us. Thank you.